And there we go. Okay, first, thanks for the invitation and thanks to everyone for staying to this last talk. I understand that we are a little bit tired and it's for the people in France, it's late. So thanks for staying till this moment. I will try not to bore you to death. I'm going to show you a trip. It's just a work that we just finished with a couple of colleagues, and it's based on a very important question that we have here at the south of Chile, which is the production of salmons and rainbow trout. And this problem and this mathematical setting that I'm going to show you started just with a conversation with a colleague from the agronomic department, who is telling us that he has a huge problem when we realized the growth of salmon and rainbow trout, because due to the presence of a parasite. This parasite is called sea lice. It's actually a little parasite that produces an infection, and once the infection is there, then you go. But as you can see here in this slide, these actually true numbers. These are measurements from different fisheries, and you have two things that you can realize really easily. The black curve, which is actually the biomass with salmon on the rainbow trout, is easily modeled by a classical ODE system, if you want. So it's like just a logistic growth curve, and the second one is a logistic growth curve with a death rate at some point. You start to recollect the fishes. That's why it goes down at this part. I'm going to change this part. You start to recollect fish, so that's why it goes down to 0. But at the second point, if you measure the parasite, you'll see that it's extremely noisy. It's really noisy in comparison. So you have two steps, and moreover, the regulatory system here in Chile, because we know that the presence of this parasite would imply a disease on the salmon or of the fish in general. If you go above certain threshold, then the government services tell you, okay, you go over the threshold, so you can get one yellow flag. If you go again, you have a second yellow flag. And at some point, if you go again, you cannot sell these fishes. That's a huge problem for the people, and the same here. So you know that you have like 2 warnings, but at the third one you are done. You cannot sell that. You have to kill all the fishes and lose the production. The same happens with any other stuff. So we were thinking about it, and we said, okay, we're interested in studying a probabilistic approach to a classic control system. We would like to write down a model that actually incorporates for example, the use of pesticides, of antibiotics that attack this parasite. We don't want to do it a lot because it also regulates the amount of antibiotics that you can use in a production cycle. And you don't want to kill all the population if you go above this threshold one time. You want to do it if you, with high probability, you are going to be in that situation. So it's not entirely classical. And our colleagues explained that to us, and we said, okay, it's easy. We can write down a local Volterra system. We have two species. We can do it in general for any species and try to control this system. But easily we realized that we did not have enough theory to tackle a problem with that perspective. So we said, okay, we have to write down something. We have to understand this. So start with the most easy question that we can think about. And that's why we said, okay, let's go into with just one ODE modeling the growth of the parasites. Only focus on the classical models for growing of a population and see if we can actually control this system. Meaning whether we can work with exponential system, logistics system, Ali factor system, Ali effect system, the theta model, ODEs that you start working with when you're younger, when you start working in mathematical biology, and see if we can say something in this context. So this is the question, that's the equation that I'm going to show you now. Is just a classical model, 1D model, and you can do it more general, but it's enough. And the formulation for the control problem is to have minimize the, for example, the use of pesticides, of antibiotics, yeah, with this constraint. And this constraint is called chance constraint. It's a chance constraint problem, because you want that the probability of our, for example, in this case, the parasite going above a safety threshold, the probability of having that outcome is small. You don't want to have all the time and all the paths that our dynamics is smaller than this safety threshold. You want to have it with a high probability. But this is what it's trying to modelize this equation here, this constraint here. But once we start working with probability, everyone here knows that you will have a lot of problems with differentiability and continuity of the stuff. Even convexity of this question is not easy to show, and that's why we realized that it wasn't not possible to start with a local Volterra general and then try to solve it. You have to start with something that we can write down easily. So in order to tackle this general problem, we propose a semi-discretization of the dynamical system. I'm going to talk a little bit about it. Formally, what we do is to take the time, make a discretization of the time, and just resolve this previous equation in any system with stepwise controls. So those are easy. You set up the control constant in any case, and then you start to solve the equation little by little, and you will end up with stuff like this. Yeah, once you do that, you'll realize that your system becomes a iterated sequence of problems that you can handle each one separately, and you have some sort of continuity that allows you to say that the ending point of the previous time is the first time of the initial condition for the next time. We make a little trick also that if you realize in the first equation, you have full generality and allow that T is not an autonomous question, but since we are making a discretization of the system, we just use a sort of independent in time, and so you have an autonomous system here that you can solve with all classical tools of OGE. And the same happens with the noise. Now we consider noise that it's constant by pieces. So that's it. Now we can write down our chance constraint control problem, which is now find a minimum of function evaluated in discrete numbers of controls. And our final constraint is just to say that the probability of having this solution smaller than this safety level is high. But now we can actually compute, and I'm going to show you this well-possession of these systems much easier than the general one. However, this is not going to be the full problem that we solve. I'm going to show you that in a little bit later. So first, now we have a system, we have a question, we have it is, if you write it down either easy, just a sequence of problems like that. And you have also a chance constraint more classical if you want. So even though the chance constraint techniques are really new in the community, so it's not that classical, but it is somehow, and you can solve it. So well-possession of the equations, what we have to ask for the equation in order to be to have a uniqueness, existence and uniqueness is classical somehow, some sort of elliptic conditions on the functions that are going inside the equation, the main equation, which is this one. But yeah, and once you have that, it's really classical to show that there is a solution, there is a pathway, unique of the solutions. But it's easily, you can see easily that most of the growth models are not Lipschitz in general. They are quadratic, cubic, or and so on and so on. So actually, the thing that you need to ask is locally Lipschitz continuity, a locally Lipschitz continuity on the functions that are involved in the dynamics. And once you have that, you can prove that since most of the equations that you know have a carrying capacity, solutions are bounded, and therefore you can go with the full system. It's kind of classical to prove it. I'm not going to go into the details, but you can see that just with a Picard iteration and with this time stop, you can pass to the general framework. So that's it for the general. You can do it for each one of the small stepwise that you plug in, and in that case, these numbers here are just constant because you're just working in one of the time intervals. You apply the previous theorem, it gives you a solution into this system. The solution is going to give you something like it. But the interesting part is not that, because that is easily done. What we actually need to prove is some sort of closedness of these sets. And if any one of you working with optimization will know that these sort of sets are important. You need somehow have convexity and some upper or lower semi-continuity in order to have solutions to the optimization problem. The dynamics is not the issue. Actually, the problem is to find a unique solution for the control. And the proof is really easily done since you are working with just one little part of the time, a small interval there. You can actually show the difference between two solutions is bounded, and the upper bound is continuous on all the parameters of the system. It's the ground well, easily, and classic. So this is going to 0, and it's going to 0 regardless the small time that you are stepped in. You're not time dependent, so all the constants that you are going to find are independent of time. And once you can solve the problem in one small interval, you can do it for all the intervals, and you will find that your full set of solutions are actually closed. It's still closed. So you are saying that actually, if you set up a safety boundary level, all the possible limits inside converge into the same set, because it's closed. So that's a main part of the well-possessedness. So at this point, we know that I'm not going to the. Moreover, the solutions are absolutely continuous, so you have everything that you want. You are in the best case scenario. And once you have that, you find that this is actually the key point of the work that we have been doing the last few weeks is this result. And this is going to be like the explanation why we work with such easy system and not with a general one. Is the main point is that you can actually write down stuffs like this. Your probability is no more having the original set and constraint was to have a probability that your solutions smaller than a safety level for all t. You can actually work with a finite set of inequalities. You go for an infinitely many inequalities to a finite one when you have all these hypotheses that we have been working with. And the proof is actually really easy. That's why I'm going to show you. But the main point of the proof is here, and it's based on this on a simple remark that we can do is that if we are working with this equation, which is actually the main idea, you can write it down in a very classical way. Then you integrate, and you have the most easy ODE trick that you explain it to your student, allows you to pass from that general formulation to this much easier formulation that tells you that all your inequalities only have to be looked at the ending point of your discretization of the system. So you're not working anymore in the continuous time. You don't have a problem in the continuous time. You have a problem in the ending points of your time discretization. And that's much easier, because if you have you now work with a finite set of inequalities in the chance constraint formulation. So the system equals post, you have this stuff, and you end up with the following system that is actually very classic, and you can solve it. So thanks to theorem 3, the probability function is now used, it's transformed to a finite number of random inequalities. Your control problem now can be seen as a regular chance constraint. So you have all these tools of chance constraint optimization problems in order to use it. Nevertheless, you still have a little problem, but it's not going to be a problem at the end of this talk. Is the fact that the dependence on the random parameter is not explicit. So in order to tackle it, what we do is take this fi, which I just explained before, and we use a deterministic version of this f function. There's several possible choices to this f hat, but all worked. That's a good point. So now the problem that you actually solved is the same DSI, the same dynamics, but with this optimization problem. Minimization of the finite stuff with phi I, where we replace this f general, which was actually something like this. We replace it by somehow the expectation of all of this. Once you do that, you lose the presence of the randomness in both sides of the inequality, which was the problem previously. The previous problem was that we have chi at the left and at the right. So once you made it random, you have everything random: the probability, the left hand side, the right hand side. That was a little problem. So that's the remark. In order to fix idea, you can think of the deterministic function the same f before, but instead of taking paths, you take, for example, the average of the dynamics, all possible solution of the previous path, and the expectation of that, you use it in order to compute the next step, and you do that for the next step and in an iterative way. And this, you can solve it. That's the good news. After all these simplifications that I've been talking about, this problem has a solution, a unique solution, and it's extremely well posed. How do you do it? First, you prove that this set has null. First you prove semi-continuity. Semi-continuity for all this for the phi, this final phi I that we are working with, and this is a finite number of phi's, because we have the discretization of the system. That makes sense why we try to pass from infinitely many inequalities to a finite number of inequalities, because now we have n phi and all of them are well based. This probability function is upper semi-continuous, and moreover, if phi I is continuous at the point u, whenever this set has null measure. And as I talked to you before, there was a very similar set that we proved that was closed. So now we use that closed in order to prove this proposition. I'm not going into the details. I'm just going to show you a little bit the idea to the upper semi-continuity. You just take a classical this set, this other one, and you have two possibilities: whether phi sigma is holds in this sense, then the inequality and the limit superior limit goes easily. On the other hand, if you have the other one, you cannot have an equality at the end. So you need to have the inequality, and that then you can use a much closer factor lemma or a Lebesgue convergence theorem, and everything goes up really nice. This stuff cannot be done when in the general case when we replace this with fi b beta general. So that's why we pass to a much restrictive formulation, if you want so. But it's not going to be restrictive anymore in a couple of slides. Before, prior to this is very classical. You use Fatou's lemma, Lebesgue convergence theorem and just the definition of upper subcontinuity, and you work with that. Some of the consequences of this weird stuff is that first, if you work with a closed subset, then this set is also closed. And this is important when you are trying to find a minimal phi. Yes, if you want to have any iterative procedure in order to find an optimal solution of this problem, you will need some closedness of the sets. If otherwise, you will end up anywhere. You want, if you start with a feasible point, find out the minimal point with a gradient algorithm, for example. If it's not closed, you're going to go anywhere. So you're not going to find a good structure at the end. Luckily, it is closed. And moreover, if you have some sort of quasi-convex CT on the functions that you start with, which are true in any of the classical models for growth population, then this set is convex. And now you have two things that everyone who works with optimization will say that are the golden goal is convexity and closedness of the sets. Yeah, if you have both, you have chances to have a solution. Then you can prove actually that if your cost function or your objective function is coercive, then you have the equivalence of these three stuffs. And the third one we have already proven in the previous results. So you actually are working with a very classic setting. But remember that you're working with somehow you cheated because you are not working with the full system that you want to work with. You make some sort of expectation over the all possibilities in order to define this f hat. So you're not done, but still this problem with f hat is convex and has a unique solution. Therefore, it's once you have a feasible point, if you start inside the system, you end up with the unique solution. But again, for f hat. But the good news and the main thing is that if you have this convexity on both the set where you look for this for the controls, UN if you want, if this is convex and if the cost or objective function that you have full freedom to take is also convex, then everything works fine. And not only that, by a feasible point of problem of general problems on 18, that is actually the problem which work with, that implies that if you have this UY, which is the optimal for this simplification of the simplification of the simplification, if you had that and you have feasibility, then it's actually the same solution for this general system. So that's the good news. Even if you're working with a simplification of the system, you are actually solving the general system. Okay, so what we're saying here is that at least when you work with this equation and when you're such that the constraint is to having that the probability of y smaller than a safety level is larger than some safety control, in that case, you have existence and uniqueness of only one control that does the good things. Meaning that at least when you simplify everything, not working with the local terra, working with only the most easy and more classical growth population models, your system has a unique solution. Your control problem has a unique solution. And in order to understand better what this means, we said, okay, let's going to do some numerics in order to understand if that makes some sense. And in order to do that, we are going to work with the as stochastic process. We're going to plug out a Brownian motion, a simple Brownian motion. Then we're working with a logistic model. And this logistic model, if you realize, it's going to be positive or negative depending on this function here, which makes a contribution from the environment. The noise for us was always the environment. So a good environment makes that the growth rate of the population is larger, and a bad environment makes that the growth rate is smaller, even negative. And we are subtracting some ponderation of this control. So you have a good environment, but if you have a large use of pesticides or antibiotics, then the growth rate of this of the population is going to be low. And if you have no control, then and a good environment, then your population is going to grow, and so on and so forth. So that's the main idea of this simulation, and it actually works. Here you have no control. And the good thing is that this is the empirical mean over, I think it was 30,000 simulations. And you see that even in that situation, some of the results of the probability and the environment are bad for this for the plague, for the parasite, and some others are very good. So it's going to the 100 kilotons very fast. And in mean, it's not good or not bad, but you grow. If you have no control into the system, then even if the environment it's not the perfect one, you're going to go to this logistic threshold. Here you have full control, meaning that you have full control. In this case was 1 in any small time interval. And in this case, you see even in a full control experiment, you might have so good environment that your population is going up also. So that's the main idea of what we wanted to do. It's even if we have the best control possible, your environment might make you in a bad situation, but with low probability. As you can see here, there's most of the curves are here. So there's a high probability of going above the threshold. And here you have a very few very small probability. Actually, it's 0 if you take 80. None of the curves go above the 80 threshold. So you have, with no control, you have that. With a lot of control, you have that. But the idea of an optimization problem is to have a sign that tells you that you don't want to control the system all the time, because probably if you do that, it's going to be very expensive, or you're going to go against the law. So you need to do something different. And that's why we consider this cost function, and we use this time multiplier, telling you if C is positive, then to control in the future is most expensive than to control in the present. And if you take C negative, to control in the future is less restrictive to control in the present. So you expect to have different outcomes. And prior to do a gradient search, we said, okay, since we are working with UN, we are taking just 0, 0, 1 to the n. So you can have control or no control. You can turn on or turn off the medicine that you're using, or the control that you're using here. As a safety level, we take 0.75, and here is the outcome. Here you have a positive cost, and you see that yeah, the smaller one might be 0, but in that case, the probability is 0.16. So you are far from 0.75. And you can see that that doesn't work, not work. This might be useful. It doesn't. This is useful. This doesn't. It doesn't. It is. So this tells you that in any case, if you want to have a 0.75, you need to control a lot of times, whether all the time, or you can shut down one of the systems, as you can see here. There's 1 0, there's 1 0, yes, 1 0, and that's it, I think, or no 0 at all. And if you compare them, you'll see that this is the best case scenario. Your cost is much smaller than the other ones. In the other case around, if you want to control in the future and not in the present, you will see that your solution is actually makes a lot of sense. Not to control the first one, which is the largest one, and then control the system all the time. So it makes sense. A lot of this makes sense, but we said, okay, but what if we are not taking now as a possible control this one? What if we take the continuous? Yes, should be much better. And it is the case. You go from, remember, 16 was the cost here, and 0.38 was here. If you allow the system to be continuous, you will find out that your optimal solution is something that is not 0, not 1, but in between, and it is growing somehow. And in that case, your final value is 0.18. Previously, it was 38. That's much better. And in the other case, you go from 16 to 8. So it's half the population. As you can see here, actually is the same. If you plot down both of the solutions, in one case, the control is going to be 0, 0, 0, 6, 0, 6. And in the other case, it's going to be 0.75, 0, 6, 0, 6, 0, 3. So here's telling you it's more expensive to control in the present. So try to use the full controllability at the end of your simulation. Here's telling you the other way around. So in one case, C is negative. I think here C is negative. Here C is positive. Yeah, absolutely. Because if C is positive, then the cost looks like this. You want to control whenever the cost is small and not in the future, which is much stronger. So now the question is, okay, we can solve the system when you have only one population. It might be multidimensional, but it's just one equation of this type, as I said many times before. Now the question for now, and the question that we haven't solved, this is everything we have been able to do so far, is what is going to happen when you consider a local Volterra system, which is much realistic in any case. But so far we have realized that just to prove the continuity of the control problem is very hard. So that's why starting with a general local Volterra was not an option. So far we have understood much better the system. So we are start to seeing some lights here, but I think we are going to need a little bit of time in order to tackle the full generality of the system. So that's it. In order to tell you, we have submit this result and just 1 week before, something like it. And now I have to do it to post it on archive in order, if you want to see much more of the details of this. There's a lot of analysis involved. As you can see, when you start working with upper or lower semi-continuity, you need to make a lot of more classical stuff, but it works. So that's it.
Thank you. Thank you, Cristóbal, for this very nice talk. So, questions in the audience? I do not see. Oh,
Pablo.
yes. Pablo and
Milan.
Yeah.
Yeah.
Thank you, Cristóbal, for your talk. Pretty interesting. Saving the salmons.
That's the main idea. Or saving exactly. the fisheries. It's much more saving the fisheries.
Yeah, well, that's right.
Going to die anywhere.
More politically correct. Yeah. So I might not have understood correctly, but it looks to me that what you're doing is you assume somehow that each discretized time is independent from the other. So
no, exactly. No, exactly. Because the next time, the initial condition for the next time is actually the end up condition for the previous one. So you have continuity.
Okay. So in that sense, there is this continuity. Because I was thinking, in the case of suppose of the control, it might, and suppose you are looking at the number of parasites, it might make a difference if you go through a kind of a series of high values.
Yeah, absolutely. Yeah,
Right.
that's
So
one of
it
the
might,
strategy.
right. So it might, but it might not be additive. You know what I'm saying?
Yeah.
So it's
Yeah.
like if you have 3 times on the peak, it might kind of non-linearly explode, and then you will have a huge thing. So it's not just the window, but this might be at the added
Yeah.
time on the past.
Yeah, absolutely right, and much more important. One of the things that we saw on the data was that actually when your population goes to this exponential growing, that is the key part when parasite can go there and make a mess. So you have to control, because if you have few fusions and you have high parasite, then all of the fusions just kill that farm.
Right.
But if you are low and start growing and you're still with low parasites, then at some point you have to control it. And the solution that is used here in Chile nowadays is actually to overuse antibiotics.
Right.
I mean, use a lot of them. Then you can control
Right.
the parasites, but it's not the actual. Here you can see making 0 or 1 is much worse than to use as some sort of continuity on the control. So use a little bit, a few, and then a little bit more, depending on how your dynamics are going. That's the idea behind the result.
Okay, thank you.
Milan?
Thank you, Cristóbal, for very interesting mixing of the ecological sustainability and dynamics. I have just one question. Can we really, can we not be afraid of uniqueness in ecological complexity? I'm afraid if something is unique because there's the only one chance, and then we will die all.
Yeah, it's a very philosophical question if you want. So
maybe some multifunction, maybe some when you solve it as a multifunction, which is unique, I'm happy because at least we have some interval, I would say variability. But if you say me like this, I'm done.
Yeah, I get your point. I think that because I'm not an optimizer myself, but most of my colleagues here at the university work on optimization, and they always want to work with convexity and so on and so forth. I totally agree with you that in ecological context, existence is important. Uniqueness, most of the time, you don't have it in real life situations. So I don't know. I'll have to think about it and see how we can tackle this problem in a much more general approach.
Muchas gracias.
No, de nada.
Carlos?
Thank you very much. I find very nice your talk. I have the following question. How do you select the time? Where do you control the system?
We just use, and here we just take this, I didn't talk a lot about it. In the simulation, it was just uniform, but the times, the system, I have to go back. Sorry, just 1 second. The problem is, actually, it's this one. No, DSI, where is DSI? Yeah. You set up this this set of chain, if you want, because as you can see here, the initial condition for the next is the ending condition for the previous one. So you actually have any discretization of the time. You can make it close or large. It doesn't matter. You need that the step is going to 0. And then you solve this equation, and the control is just constant by pieces. So you do not choose. You don't choose which controls you are going to use. It's just the algorithm is going to tell you which one is the ending system, because what we proved is that there's existence of uniqueness of this stepwise control that makes you the best on the smaller cost function. So you let the system talk to you. You do not choose in what time you're going to control. The system is going to tell you, the solution of the dynamical system is going to tell you which one is the better time to control the system, and which is the size of the U that does this control.
And then in your simulation, you chose some times. This time was computed by the algorithm, or was given?
No, the times you set up the times, because in what we do know is that the data is taken weekly, so you know that the time frame is 7. So in our simulation, we take a discretization of 7 days for each one of the controls.
And in practice, do you have some observation of the system in order to optimize the time? Where do you control the system?
Actually, in general, if you can write down another equation where the cost is related to the time. If you're interested in knowing which time you have to control, you can write down a different system where this phi might depend on random times. We'll have to think about it. But it's a nice question, yeah. In order to say, yeah.
If you have a random noise, or you have a noise,
yeah,
in a stochastic process, the solution of the logistic model can be very different from noise to noise.
Absolutely.
If you select in everything the same times, maybe it's not very optimal.
Yeah, but just that is just for the simulation, just for a numerical example, because the solution is for any time discretization.
But deterministic.
Yeah, that
is the point.
Yeah, that's a good point. Yeah.
That is
yeah,
okay. In any case, I find very nice your work. Thank you very much.
Yeah, what we did actually was to prove the consistency between the discretization, the time discretization, and the limit. So we can work a little bit on that, because if we know that this discretization now it's somehow it's also probabilistic, then, but if you know that the 2 times are going to 0, then you might have the same sense of convergence.
Yes, but I imagine that in practice, do you have to do some kind of measurement? And using this measurement, you have to adjust the control, because if no,
yeah, I get it. It's a nice
maybe this random time can say you when you have to take the measurement.
Actually, it's a nice extension of the work, because now we work with this time, deterministic time discretization, but we know that we can solve it. The next step would be, what if we make it probabilistic and try to see if our technique still works? It's a nice.
I think that a lot
of perspective. Yeah.
I think that a lot of things that you told maybe work. I think that will work.
Yeah, must be. Yeah, absolutely.
Okay, thank you very much.
Yeah. So, well, we wait for the results on Lotka Volterra.
Hopefully, but I think that the question that Carlos just asked is much more interesting and tackled in a shorter time period than the general Lotka Volterra question.
Yes, because indeed the problem of measurement the control will be very sensible to the measurement you are taking.
Yeah. To which measurement and when you do it.
Yes. So Pablo wants to
ask a comment, because just a comment in terms of well, two comments, but very quickly. I don't know if the salmon example is the best. Because actually, because those are cage animals, and they are put there, they don't have a population dynamics. They just grow in size because they are getting fatter and fatter and fatter.
Try to isolate them. Yes.
Right. And if anything, it's just a death process, because the population is just diminishing in numbers, but it's increasing in biomass as a total. So watch out with that kind of, yeah. And the other is can you introduce constraints on this model? Suppose that we are with an animal like have a reproduction, and you are using antibiotics to control a virus or a bacteria, whatever. A bacteria have to be if you use antibiotics. Then suppose that you don't want to use more than a certain amount of antibiotics because the law doesn't allow you to go beyond a limit. So can you introduce also these constraints and see how it's affect your solution?
Actually, so far it's included because you just have to say that your control is smaller than something. So you can plug it into this PI.
Okay. Right.
Optimization. You can put it whether there or on
in the cost
more constraints. Yeah, but if it's just on the control, then you plug it into like a penalty into this fee. And if you go above some threshold, then your cost is infinite. That remains convex, so you still have all the results. So it's just there at this point.
Yep. Thank you.
Okay, so Carlos